And we're back. Welcome back and happy Tuesday. Today, we will continue on with our discussion of the transport layer with our focus on a number of things: connection establishment, connection teardown, as well as principles of congestion control. But before we begin, some administrative bits. Project number 3, a simple web server, is due Friday. Please note that down, Friday, the 5th of March at 12 noon. Please make sure you note that on your calendar. It is not the usual 11:59 and 59 seconds. It is Friday, the 5th of March at 12 noon. Written exam number 1 will be Tuesday, the 9th of March, a week from today at 12 noon. We will go over the questions at the outset of class, and you will have about 30 hours to work on it. All right, so why don't we begin? When we last left off, we talked about TCP's fast retransmit. And this fast retransmit looked at triple duplicate acts as a kind of shortcut to trigger the resend of a lost packet before the timeout occurred. And so the idea is that if you get duplicate acts, it means that that packet was not successfully delivered by the receiver endpoint. So why don't we continue, and let's look at flow control. Now in flow control, from the perspective of the receiver, we have our segment coming in from the network layer at the receiver endpoint, and that data from the segment might be coming in slower at the receiver than the sender is pushing them out on the other endpoint in this communication. And so we said out of order packets are stored and assembled, put back in order in the buffer at the receiver side transport layer runtime. And the application process above removes data from these buffers through the TCP socket. And so with this, one of the things that you don't want to happen is that you don't want the sender to overwhelm the receiver. If the sender sends packets faster than the receiver can push them up to the application layer above, or more correctly, the application layer above can retrieve them from the buffers in the transport layer below, then eventually the transport layer runs out of buffer space. And so it makes no sense to keep sending data faster and faster and faster, increasing the pipeline, if there's no place to put those packets on the receiver. And so what flow control is the receiver gives information back to the sender, and that information is used to modulate or control the sender's send rate by forcing the sender to adjust its window size. And if it adjusts its window size, makes it smaller, it means that its effective send rate is going down, it's decreasing. And so what it does is it sends this information back to the sender. And it does so because it doesn't want the sender to overflow its buffers by transmitting too fast. And so this is called the receiver window. And the receiver window is a piece of information that the receiver advertises back to the sender in the TCP header in the direction going from the receiver back to the sender. And so the receiver buffer in most or many implementations, the popular default size is 4096 bytes. And some operating systems will adjust this. But 4096 has sort of been the standard that you'll see for packet sizes. And so what the sender does, then it sends receive window, which is the amount of free buffer space out of that receiver buffer size 4096, that free buffer space that is available. And so when the sender gets this receiver window number back from when the sender gets this receiver buffer data back from the receiver, it then uses that to limit the size of the window, which is the amount of unacknowledged packets that are allowed to be in flight. And so what this does is it guarantees that the sender will send no more packet data than can physically fit in the available buffer space on the receiver side transport layer runtime. So if we look at the TCP segment structure, the receiver window field is exactly that, the RWIND receiver window spec associated with the free buffer space on the receiver side transport layer endpoint. So let's take a look then at connection management. Now, of course, in order to exchange data, both the sender and receiver endpoints have to guarantee that each other has established or set aside the correct resources needed to engage in this reliable data transport. And each endpoint has to know that the other side is willing to do this, willing to establish this connection. They have to also agree on the parameters needed in order to engage in all of the things dictated by TCP. And so here we have the application layer, and we have a socket up above, and that socket straddles, as we said earlier, the seam between the transport layer and the application layer. And so when you create a client socket to initiate a communication, and you create a server socket, or a welcome socket as the book calls it, and accept the connection, underneath the covers there are messages that are exchanged, and these messages are part of the connection establishment, the validation, if it were, between the sender and the receiver, the different endpoints, the validation that they are able to engage, i.e. allocate the resources necessary to engage in reliable data transport. So all of that happens before you actually do the send, and it happens on your behalf. And that's part of the creation of the sockets, and that's performed for you by the TCP runtime in the endpoints for the communication. And so that includes things like the sequence number, going from the client to the server and server back to the client, the sender and receiver buffer sizes. It also talks about the timer resources, etc. And so when you establish this connection, you need to communicate, and this is through a connection establishment message. And so in the book, they talk about flaws with the so-called two-way handshake as the basis for the description or the creation of the so-called three-way handshake. And so essentially, we have two parties, let's say Alice on the left, Bob on the right, and Alice wants to talk to Bob. So Alice then sends a message to Bob and says, hey, let's talk. And when Bob answers, okay, that means Bob is ready to engage in a conversation. Now, of course, the computer equivalent, you have a machine on the left here, a client, and a server, another machine on the right. So the client chooses some piece of information, like a sequence number. It requests a connection, and the server gets that connection request and says, okay, let me establish the resources I need on my side in order to engage in reliable data transport. And it sends back the acceptance of that connection, yeah. And so once that connection is accepted by the client machine, it knows the server has established its resources, so the client goes ahead and says, okay, well, let me establish my resources. But there's a problem with this, because the problem is that the server, this machine on the right-hand side, it has no idea about the establishment of connection state and resources that the client has performed. It doesn't have any validation of that. And so you can have some failure scenarios associated with these two messages to establish connection state and resources, the so-called two-way handshake. And so here, at some point, the client is going to terminate its connection. Once it's established, the client engages in communication with the server, like an HTTP request message and an HTTP response message. And the server also forgets this connection. But what happens then, after you're established, maybe there was some congestion or maybe a timeout fired, and you had a rebroadcast, a retransmit. So if you retransmit, all of a sudden, well, that's not an actual connection, it's just a retransmission of the connection request. Once the server has forgotten about the connection, maybe it's done communicating, it's closed its side of the endpoint, it sees this retransmit and goes ahead and reestablishes all the resources that it needs to engage in reliable data transport. Now, of course, there's no client on the other side, and you have something called a half-open connection. Only one of the endpoints, the server, has established its resources, but there's really no connection involved because the client didn't really initiate this. It was because of a retransmit. And we know at this juncture a retransmit can occur because it's taking too long to receive back the response. Okay, so let's take another look at this two-way handshake. And the first two messages, the round trip, we have the forward connection request. The server establishes its resources. It returns back an acceptance of this connection. And so now the client gets this confirmation from the server, and it goes ahead and says, okay, let me establish my resources, and I'll send data. So it sends data, and the server, because it's established its connection at this juncture, it goes ahead and accepts this data. All right. So now the client terminates, the server forgets its side of the connection, and all of a sudden there's a retransmit of both the connection request and the data. And so now, okay, the server reestablishes its resources and then goes ahead and accepts this data, but there's no client on the other side to engage in this communication. Again, this was a retransmit, and there's no client there. Another half-open connection scenario. And so let's look at the three-way handshake, how this is different. Now, the three-way handshake includes not only the connection establishment from the client, the response for accepting that by the server, but it also has another message from the client back to the server so that the server can confirm that the client has established its side. And in giving that third message, giving the server validation that the client established its resources, it knows if the client is actually there or not. So let's take a look at it. So here we have the connection request, and this connection request is a special segment called a synchronization message, a SYN message. So the SYN bit is set in the TCP header, and it chooses a sequence number X. And so now the client goes from the listening state to the SYN sent. It knows it sent the connection establishment or the synchronization message. The SYN bit has been set. So now the server gets this SYN message, says, okay, let me go ahead and establish my resources in order to engage in reliable data transport. It chooses a sequence number, let's call it Y, and it sends back a SYN acknowledgement, the so-called SYN ACK. So the ACK bit is set in the flags in the TCP header or in the transport layer header, as well as the SYN flag is set. So it sends the SYN ACK, and it also sends its sequence number on its message area and payload for the SYN ACK segment going back to the sender, back to the client machine. And so it also computes an acknowledgement. And this acknowledgement, you'll notice, it's one more than the sequence number X that it got on the message on the forward path from the client machine to the server machine. And because it's X+1, when the client gets it, it says, aha, the server must be live and operating because it incremented my sequence number that I sent it by 1. So once this SYN ACK comes, the client says, well, the server must be live and must have allocated its resources because it knew how to add 1 to my sequence number. Okay, so now that the client gets back this acknowledgement, it knows the server has established the resources, the responsibility on its side of this TCP runtime responsibility for reliable data transport. So now then the client machine says, all right, well, it's established, so let me go ahead and send an acknowledgement for the SYN ACK to let the server know that I received the SYN ACK and also that I've established my resources. So it sets the ACK bit, and then it sets the ACK number to Y+1. And when the server gets that ACK number Y+1, it says, aha, the client received my acknowledgement and it has established its resources, and I know it's live and ready to go because it incremented my sequence number by 1 in the ACK. And so this indicates, this act, that the client is live and available and ready to satisfy its obligation in the reliable data transport. And so this segment, this acknowledgement of the SYN ACK, you could call it the SYN ACK, might also contain as piggyback the initial segment worth of data that's going from the client to the server. Because why waste a segment, why waste a packet if you can put real data in it, then go ahead and do that, in addition to acknowledging the SYN ACK. And now the server, once it sends its ACK, it says the SYN message has been received, and then the connection has been established with the client once you get confirmation back from the client with the SYN ACK acknowledgement that the client is live. And now the communication is guaranteed. You don't have this half-open communication issue. All right. So let's look at a finite state machine. And in this finite state machine, it describes the sequence of events that occurs in the server side, that's the path on the left-hand side, and the client side, that's the path on the right-hand side. So here we have the client server, and the server sitting on its welcome socket, its server socket, and the client creates a new socket. So when the client creates a socket, it sends the SYN message, and it goes to the SYN sent state. So then the server, it sits on its welcome socket or server socket, it accepts the connection. So once it gets the SYN message from the client, it sends the SYN ACK with its sequence number and ACK X+1, which is an increment of the SYN message on the forward path from the client. So we have the client over here and the server behavior over here. So now that the SYN ACK was sent, the server transitions to a SYN received state, and it's waiting back for that SYN ACK from the client. So the client then gets the SYN ACK from the server. It knows the server is live, and it sends the ACK number back to the server. Server gets that ACK Y+1, which is an increment of its sequence number, and they're both now established in their connection. All right. So when you close a connection, the client and server each close their side of the connection. And this triggers the sending of a so-called FIN packet, TCP segment, where the FIN bit is sent, FIN as in finish. You're closing or tearing down the connection. Go ahead and start the process of reclaiming all those resources that were allocated to engage in reliable data transport. Now, you respond to receiving a FIN with an ACK. And on receiving a FIN, the ACK can be combined with its own FIN message. You have to acknowledge the other side that, yeah, you got this FIN message, and you're going to tear stuff down, tear down your resources, reclaim them. Simultaneous FIN exchanges can be accommodated in the teardown of a connection. So we start out and we have established state, this establishment of the connection between client and the server. And so the client then closes its socket. When you close the socket, it transitions to the FIN wait 1 state. And at this juncture, the client can no longer send data, but you can have incoming data. Now, when I say no longer send data, what I mean is that the application layer cannot do an RDT send from above. So no data from the application can be packaged for sending out by the transport layer on the client side. So that triggers a FIN packet to be sent with a sequence number. So the server gets this FIN packet, and it goes into the closed wait state, and it sends the ACK for the FIN. It's called the FIN ACK. And so when it acknowledges this FIN ACK sent by the server back to the client, you'll notice the ACK number is incremented by 1. So the client knows, yeah, the server got it because it did something in response. It incremented my sequence number on the forward path. It incremented it by 1. So now the client transitions to this FIN wait 2. It's now waiting for the server to close its side of the connection. And so here, the server can still send data. So it sent that ACK. Now, of course, at some point, the server closes its connection. And when the server closes its connection, it can no longer send data anymore. And that triggers a FIN bit in the opposite direction, going from the server back to the client. Now, in the meantime, the client waits for the server to close, and then once it gets that fin message from the server that the server is closing or tearing down or getting ready to tear down its side of the connection, it goes into a timed wait period. And when it goes into that timed wait period, an ACK for the server's fin is sent. And this is sent by the TCP runtime or the transport layer runtime, not by anyone acting on the socket. At that point, when the close happens, the application can't send data. So the timed wait responds to this fin with an ACK, the fin from the server with an ACK. And so the server can no longer send data, but it can receive data. And then when it gets that ACK, it closes the connection, and the two connections are officially closed. All right. So let's turn our attention to principles of congestion control. We're going to look at why congestion happens from the perspective of the perceived end-to-end throughput called the Goodput between the applications above. And so congestion informally means that you have too many sources sending too much data faster than the network can handle it. Now, congestion control is different from flow control. Flow control, we're slowing down the sender to match the amount of buffer space in the receiver. But with congestion control, we're slowing down the sender in response to a network that cannot handle that rate of data. And so how does this manifest? You have lost packets, and you also have long delays, because queuing delay in the router buffer goes up as you get more and more packets being added to the buffers. They're waiting in line longer. And congestion control is one of the top problems in computer networking. And so in this diagram, we have two senders and two receivers, and we list the 5-layer internet stack for sender and receiver endpoint. So here we have host A sending to one of the servers on the right-hand side, and it goes through a single router. And this is the idealized case where you might have a router with an infinite amount of buffer space. That means you're not going to have any packet loss. And so lambda in is the data rate from the application layer on the sender, host A, down into the transport layer. And lambda out is the throughput, the rate at which data comes out in the application layer on the destination endpoint. And so let's imagine you have an output link capacity of bandwidth R, transmission rate R, and there's no retransmission of data. So in TCP IP, they share the bandwidth, and so each of these connections between host A and the server and host B and this bottom server is going to use R over 2 capacity of that link. And so here we have lambda out and we have lambda in. As lambda in approaches R over 2, the link capacity, the lambda out, the rate at which we get packets emerging in the application layer at the destination endpoint, lambda out is going to also be R over 2. If there are no retransmissions, that means the same amount of data being pushed into the network is also the same amount of data coming out of the network. And so we get this 45-degree line, and then eventually it saturates once we use that full R over 2 of the available bandwidth to this end-to-end communication between host A and that upper server. And so if we exceed R2, you'll notice that it's only R2, the rate at which it outputs. That does not linearly increase anymore once you saturate your fractional bandwidth R over 2 bits per second. Now, if we look at the delay at the router, that delay is going to increase. If we approach the full link utilization, well, eventually we have to queue more and more packets, and it's going to take longer, the delay that we experience for this end-to-end flow between the sender and receiver endpoints. And so you get large delays as the arrival rate, lambda in, approaches the capacity for that link. Now, let's take a look at one router, and we'll look at the case. We have a finite buffer. Now, of course, when you have a finite buffer, as the rate of transmit increases, that buffer is going to fill up, and you're going to drop a packet. So the sender retransmits in the case of timeout because you have packet loss at the router. That packet gets dropped if it meets a router buffer that is full. And so the application layer then inputs data at a rate of lambda n. But as we said when we looked at the principles of reliable data transport, that the transport layer maintains a copy of that segment because it might need to resend it. And so we have the rate of send into the network by the transport layer is going to be, we call it lambda n prime. And that includes the original rate lambda n from the application layer plus the retransmits. And so it is necessarily the case that lambda n prime, the rate at which the transport layer pushes data into the network, is going to be greater than or equal to lambda n, the rate at which the application layer above it pushes data into the network, because the transport layer includes the retransmits. Okay, so let's take a look at the idealized scenario, that the sender only sends when the router buffers are available, when there's space to store them. That means lambda n and lambda n prime are going to be the same because there are no retransmits. And so we start out and we have a packet. It goes into the transport layer, makes a copy, it sends it into the network layer, free buffer space at the router, it makes its way out, and then it's delivered to the destination endpoint at the rate lambda out. And so if we look at this, we get the following scenario. The throughput, lambda n, pushing data into the network, goes to R over 2, the full fractional use, half of the bandwidth of that link, and the output remains equal up to R over 2, so you get this 45-degree line. It's a linear increase. But what happens when you have packet loss? When you have packet loss, now lambda n prime will include retransmits. So lambda n prime is going to be greater than lambda n. So you start out, you send into the transport layer, make a copy, it goes into the router, there's no buffer space, it gets dropped. So then you send a copy, retransmit, maybe there's free buffer space in the router this time, it makes its way through, and then gets delivered at a rate lambda out. And so if we take a look at this graph, at the relationship now between lambda in prime and lambda out, now as lambda in prime starts to approach the link bandwidth, you start to see this elbow in the graph. Because as you approach the saturation of the link bandwidth, the transmission rate, you're going to start to get dropped packets as those router buffers build up and fill up. And that drop packet means that effectively your lambda out is going to get smaller. And that's where this gap comes in. And so you're going to start to see an elbow here because that send includes the retransmissions. Now, certainly, end to end, you're going to get less bandwidth because that lambda in prime includes the original data from the application layer plus the retransmits due to packet loss. And so that means as you approach fractional usage, R over 2, your perceived output is going to decrease, and that gap is due to the retransmits. The other thing that you can have is duplicates. And of course, when you have duplicates, it looks the same. You reduce the effective output lambda out at the destination application layer. And so if you transmit to the transport layer, make a copy, you send that packet through, and let's say there is free buffer space, but the queuing delay is quite large. And now before it makes its way, the timeout fires, and then a duplicate is sent. Now if that duplicate is sent, what happens? Well, the duplicate is dropped by the receiver transport layer runtime because it does not deliver duplicates. That would be catastrophic for many applications. And if we look at the performance chart, again, we see the same shape as the effective rate of data going into the network from the transport layer, lambda in prime, approaches saturation. The router buffers start to fill up. There's higher queuing delay. The timeouts begin to fire, and then it retransmits. And so that effective rate, lambda out, at the endpoint application layer, for which packets emerge from the network, that's going to be reduced. And that gap, we see an elbow in the graph, it bends, and that gap is due to the retransmit. And that retransmit, you still pay the cost, but you don't have the effective benefit from it because it's a duplicate. All right. And so the cost of congestion means that there's more work for a given goodput. Now, goodput is different from throughput. Goodput is a perceived end-to-end rate, which is not the same as the rate at which the application is sending, which is not the same as the rate that the transport layer on the sender side is sending, because it can include duplicates, and you only get one packet's worth of benefit whenever you send a duplicate. So that ends up in a reduced end-to-end bandwidth perceived by the receiver endpoint, lambda out, at the destination application layer. So the other cost of congestion might have to do not with you sending, but someone else sending. If you have fractional usage of a link, that fractional usage from someone else's pathway between source and destination endpoint can result in buffers on the routers filling up. And so here we have 4 senders going to 4 receivers, and we have so-called multi-hop paths. And so here, host A is sending, going across that top router, going across that right-hand router to destination host C, and then host D is going across that left-hand router, going across that top router to get to destination endpoint B. And so here we measure lambda in for host A, lambda in prime for the transport layer on host A, and we're also looking at lambda out for host B. Now, of course, lambda in and in prime are a different host on a different end-to-end path than lambda out on host B. Lambda out host B is on the end-to-end path between host D and host B, and lambda in and in prime on host A is on the endpoint for the flow between host A and host C. But one of the things you notice is that that blue path, it shares the top router with the red path. And so an increase in send rate for host D along the blue path is going to impact that top router's queuing, that buffer space. It's going to fill up if host D increases its send rate. And that's going to impact the end-to-end path along the red path between host A and host C. So if we look at this relationship, if we increase lambda in and lambda in prime, that's going to have an impact on lambda out, because that increase in lambda in prime due to retransmits is going to cause the queuing delay for that top router to increase, as well as the buffers to fill up in that top router, and that's going to impact lambda out, the packets emerging on host B along the blue path from source D. And so as the red lambda in increases on the red path, all the arriving blue path packets at the upper queue are going to be dropped because of that upper router's queue filling up. So that means as you increase lambda in prime on host A, that's going to cause the throughput for that path between host D and host B to go to 0. And so your goodput is affected not only by your send rate and your retransmit rate, it's also impacted by the send and retransmit rate of other flows on the network that use the same routers on hops between their source and destination along their path. Okay, so another cost of congestion concerns when packets are dropped. Now, of course, if you have a number of hops between the source and the destination, it becomes more and more expensive the closer to the destination that packet gets before it's dropped. And so when packets are closer to their source, let's say I have one hop, and I have another hop, and I have another hop, and I have another hop, and then I have my destination. There's my destination, and here's my source. Now, of course, if I get a packet loss at the first hop router, it's not as expensive as if I get packet loss at that last hop router, because I've paid the cost end-to-end of going across all those routers in between. And so when a packet is dropped at a so-called upstream router closer to the destination, the transmission capacity that was used for that packet all along the way is effectively wasted. And so another cost of congestion, it increases the closer and closer that congestion causes packet loss, the closer it gets to the destination across a series of hops. Okay, so with that, that's all I had for today. We'll end there. And as usual, please stay healthy, stay safe, and I'll see you all on Thursday.